Right now, at this very moment, the universe is growing. Every galaxy you cannot see, scattered across the unimaginable dark, is rushing away from every other, the vast spaces between them stretching wider with each passing second, the whole cosmos swelling outward in a silent, ceaseless expansion that has been going on for billions of years. This is not a theory. It is one of the most firmly established facts in all of science. The universe is expanding, growing larger, the galaxies flying apart, and they have been doing so for almost the entire history of everything. Look up at the night sky, and you are looking at a universe. In the middle of a colossal, slow-motion outward rush, every distant point of light receding into a greater and greater distance. But here is the question that has haunted cosmologists for nearly a century. The question that sits at the very heart of the fate of all things. Will it last? Will the universe simply keep expanding, forever growing colder and emptier and more spread out until the end of time? Or could something stop it? Could the expansion slow and falter and halt and then terrifyingly reverse? Could the entire universe, having spent billions of years flying apart, begin to fall back together? The galaxies that had been racing outward, suddenly turning and rushing back toward one another, faster and faster. The cosmos collapsing in on itself, the great expansion running backward, until everything, all the matter and energy in all of existence, came crashing together in a final, violent, all-consuming collapse. Sit with that image for a moment, because it runs against everything our instincts tell us about the cosmos. We are used to thinking of the universe as a place of permanence, of slow and stately processes, of stars that burn for billions of years and galaxies that drift in their courses with serene indifference. The night sky feels eternal, fixed, a settled backdrop that will always be there. But the Big Crunch asks us to imagine the opposite, a universe that is not a permanent stage, but a temporary event, one that swells outward for a time and then collapses back. The whole magnificent cosmos, a passing episode between two states of unimaginable density, the grand expansion we live inside. Merely the first half of a story whose second half is a headlong fall back together. It is a vision of the cosmos not as an everlasting thing, but as a single vast breath, drawn in and then released, expanding and then collapsing, with everything we know taking place in the brief pause at the top of that breath. And what makes the Big Crunch so compelling and so worth understanding is that it is not a fantasy invented to frighten. It is a genuine scientific scenario, one that follows directly from the real physics of the expanding universe that was for decades considered one of the two most likely fates of the cosmos, and that, as we will see, has recently come back into serious discussion after a period when it seemed to have been ruled out. This is not myth or metaphor. It is a real possibility about the real fate of the real universe, grounded in observation and theory, debated by serious scientists, hanging on questions that telescopes are working to answer right now. To understand it is to understand something true and profound about the kind of cosmos we live in, and about the deep uncertainty that still surrounds the ultimate destiny of everything. This is one of the most dramatic theoretical fates the universe could face, and it has a name. It is called the Big Crunch, and it is the mirror image of the Great Expansion. The possibility that the cosmos does not drift quietly into the cold and the dark, but instead slams shut, reverses, and crushes everything back together into an unimaginably hot, dense finale. Imagine it, a sky that, instead of growing emptier, begins to fill with approaching light. Galaxies that, instead of fading into the distance, swell and brighten as they rush back toward you. A temperature that climbs and climbs. A universe folding back in on itself, all of its vast structure collapsing inward, accelerating toward a single, searing, crushing endpoint. The expansion of all things, played in reverse, ending not in a whisper but in an inferno. It is the kind of idea that once you have truly pictured it, you cannot quite shake, because it inverts the deepest assumption we carry about the universe. The assumption that it will always be roughly as it is, vast and open and quietly enduring. The Big Crunch says that this openness, this vastness, this quiet endurance might be temporary, a passing phase, and that the same gravity which gently shapes the orbits of planets and the drift of galaxies might, on the largest scale and over the longest time, be slowly gathering itself to undo the entire expansion and bring everything crashing home. It asks us to see the calm, spacious cosmos not as a permanent condition, but as the high pause of a great breath, beautiful and temporary, destined perhaps to be released. Tonight, we are going to explore this possibility in full, one of the great theoretical fates of the cosmos, and we are going to understand it not as a vague nightmare, but as a real scientific scenario, grounded in the actual physics of the expanding universe. We are going to learn why the universe is expanding in the first place, and what could ever cause that expansion to stop. We are going to follow the cosmos through the terrible turning point, the moment the expansion halts and begins to reverse, and watch as the galaxies turn from fleeing to falling. We are going to descend into the collapse itself, the sky brightening and heating, the structures of the universe destroyed. One by one, the matter crushed back toward the state from which it came. We are going to face the final, crushing finale and the honest truth about how little we know of what happens at the very end. And then we are going to confront the surprising and modern twist. In this story, the way a great discovery seemed to rule the Big Crunch out, and the way recent tentative hints have quietly opened the door to it again. But to understand how the universe could collapse, we first have to understand how it is expanding. Because the collapse, if it ever comes, would simply be the expansion running in reverse. And the story of how we learned that the universe is expanding at all is one of the great revolutions in the history of human thought, a moment when our entire picture of the cosmos was overturned. For most of human history, people assumed the universe was static, fixed, eternal, the same as it had always been and always would be. The stars were thought to be permanent fixtures, the cosmos a stable, unchanging stage. But in the early 20th century, astronomers studying distant galaxies noticed something strange and profound. The light from those galaxies was shifted. Its colors stretched toward the red end of the spectrum in a way that indicated the galaxies were moving away from us. And it was not just a few of them. Nearly every galaxy, in nearly every direction, was racing away. And the farther away a galaxy was, the faster it was receding. The most distant galaxies were fleeing at the most tremendous speeds, while nearer ones drifted away more slowly. a clear and unmistakable pattern. It is hard from our vantage point today to appreciate how shocking this was, because we have grown up knowing that the universe expands and it no longer surprises us. But to the people who first uncovered it, it was almost unbelievable. A finding so contrary to the assumed eternal stillness of the heavens that some of the greatest minds of the age resisted it, looked for errors, sought ways to explain it away. The idea that the entire universe was in motion, that the cosmos itself had a history, that it had been different in the past and would be different in the future, overturned on assumption so deep and so old that it had rarely even been stated. The assumption that the universe simply was, fixed and permanent, the unchanging backdrop against which everything else happened. To discover that the backdrop itself was moving, swelling, evolving, was to pull the floor out from under the oldest picture. And it took time for even the scientists who found it to fully accept what their own measurements were telling them. But the evidence was overwhelming, and it only grew stronger with time. Galaxy after galaxy, in every direction, astronomers looked, showed the same telltale stretching of its light, the same recession, the same pattern of more distant meaning faster. There was no escaping the conclusion. The universe was expanding and had been for an immense span of time, and this single fact reshaped all of cosmology, transforming the study of the heavens from the contemplation of an eternal, static order into the investigation of a dynamic, evolving cosmos with a past and a future, a beginning to its expansion, and perhaps an end. Everything we now understand about the fate of the universe, including the possibility of the Big Crunch, flows from this foundational discovery that the cosmos is not still but in motion, not fixed but growing, the galaxies forever drifting apart on the swelling fabric of space. This pattern, that everything is receding and that more distant things recede faster, is exactly what you would expect if the entire universe were expanding, if space itself were stretching, carrying the galaxies apart like dots drawn on the surface of a balloon that is being inflated. As the balloon grows, every dot moves away from every other dot, and the farther apart two dots are, the faster the distance between them grows. That is precisely what astronomers saw in the galaxies. The universe was not static after all. It was expanding, swelling, the space between the galaxies growing with time. And this discovery shattered the ancient picture of an eternal, unchanging cosmos and replaced it with something far stranger and more dynamic. A universe with a history. A universe that was different in the past and will be different in the future. A universe in motion. And it is worth being precise about what this expansion actually is, because it is easy to misunderstand. The galaxies are not, for the most part, flying through space the way debris flies out from an explosion. Rather, the space between them is itself growing, stretching, expanding, and the galaxies are carried along with it. It is space itself that is swelling. This is a subtle and profound idea, that space is not a fixed, inert stage, but a dynamic thing that can stretch and grow, and it lies at the heart of our modern understanding of the cosmos. The universe is not expanding into anything. There is no outside that it is growing into. It is simply that the distances within it are all increasing. The fabric of space stretching everywhere at once, the galaxies riding along on that swelling fabric, drifting ever farther apart. This is a subtle point that rewards a little more attention, because it changes how you should picture the whole scenario of collapse. Since it is space itself that expands, carrying the galaxies along, a collapse would not be galaxies flying back through space toward a single location, like objects falling into a drain. It would be space itself contracting, shrinking everywhere at once, so that every galaxy draws closer to every other galaxy, not by traveling toward a common point, but by the very distances between them all, decreasing together. There is no special center toward which everything would fall, no single place where the collapse would happen. The contraction would occur everywhere simultaneously, the whole fabric of space shrinking uniformly, every distance diminishing at once, so that from the vantage of any galaxy, all the others would appear to be approaching from every direction. The collapse, like the expansion, would have no center and no edge. It would be a property of space itself, the entire fabric drawing in, rather than a rush of objects toward a point. This is genuinely hard to picture, because we have no everyday experience of space itself changing size. In our daily lives, space is the fixed and unchanging container in which things move. But on the largest scales, space is not fixed at all. It has been stretching for billions of years, and it could, under the right conditions, contract. To imagine the Big Crunch correctly is to imagine not galaxies hurtling inward through a static space, but space itself shrinking, the container collapsing along with its contents, the distances of the whole universe winding down together. It is the stage itself that would fold up, not merely the actors rushing to its center, and that makes the collapse a far stranger and more total thing than any ordinary falling together could be. Now, this expansion has a remarkable consequence when you think about it in reverse. If the universe is expanding, growing larger with time, then in the past it must have been smaller. And if you run the clock back far enough, the galaxies would have been closer and closer together, the universe more and more compressed, denser and hotter, until billions of years ago, everything would have been packed into an extraordinarily hot, dense state. The entire observable cosmos compressed into something almost unimaginably small and fierce. This is the picture we now have of the early universe. An exceedingly hot, dense beginning of the expansion, from which everything has been growing and cooling and spreading out ever since. The expansion has been running for billions of years, the universe steadily growing, larger and cooler, the galaxies forming and drifting apart, all the way to the vast, cool, spacious cosmos we see today. This rewinding picture, the universe growing smaller and hotter as we run the clock backward, is one of the great achievements of modern cosmology, and it is grounded in solid evidence, not mere supposition. The faint background of radiation that fills all of space, detectable in every direction, is understood as the cooled afterglow of that hot, dense early state, the leftover warmth of the universe's fiery youth, stretched and cooled by billions of years of expansion into the faint chill it is today. The relative amounts of the lightest elements throughout the cosmos match what would have been forged in the heat of that early universe. Many independent lines of evidence converge on the same picture. A universe that began its expansion in an exceedingly hot, dense state and has been growing and cooling ever since. The expanding universe is not a guess. It is one of the best supported descriptions in all of science. And it is the firm foundation on which any discussion of the universe's fate, including the Big Crunch, must rest. And it is precisely this well-established history of expansion that makes the question of reversal so natural to ask. If the universe has spent billions of years growing from a hot, dense state into the cool, spacious cosmos of today, then the obvious question is whether that growth will continue forever or whether it might someday stop and reverse, sending the universe back toward the hot, dense state from which it came. The Big Crunch is, in essence, the hypothesis that the expansion is not permanent, that the great growth we observe is the first half of a story whose second half is contraction, the universe destined to retrace its expansion in reverse and return, at last, to something like the fiery density of its origins. It is a question that arises directly and inevitably from the established fact of expansion, the natural counterpart to everything we know about the universe's growth. So we live in an expanding universe, one that began its expansion in a hot, dense state and has been swelling outward ever since. And this immediately raises the question of fate, the question we are concerned with tonight. Because an expansion, like anything in motion, is subject to forces. A ball thrown upward is moving away from the Earth, but gravity is pulling it back, slowing it down. Whether it escapes into space or falls back to the ground depends on the balance between its upward speed and the downward pull of gravity. The expanding universe is, in a sense, in the same situation. It is flying outward, but gravity, the mutual attraction of all the matter in the cosmos, is pulling inward, trying to slow the expansion down. And the ultimate fate of the universe hinges on the outcome of this cosmic tug-of-war, on whether the outrush or the inward pull wins in the end. To understand the Big Crunch, we have to understand this struggle, the battle between the expansion and gravity, on which the fate of everything depends. It is a strange and humbling thought that the destiny of the entire cosmos comes down to something as simple, in principle, as a contest of speed against pull, the same kind of contest that decides whether a thrown stone falls back or escapes. The grandest question imaginable, how everything ends, reduces at its heart to a balance between two quantities. How fast the universe is flying apart, and how strongly its matter pulls it back together. There is something almost absurd in the simplicity of it, that the fate of all the galaxies, all the stars, all the matter and energy that exists should turn on so basic a competition. And yet, that is genuinely how it works, at least in the classic picture. The universe is a thing in motion, subject to a force, and like anything in motion subject to a force, its future depends on whether the motion or the force prevails. What makes the cosmic version so much more profound than a thrown stone is that there is no ground for the universe to fall back to, no earth waiting below. When the universe collapses, it does not fall toward anything outside itself. It falls toward itself, every part rushing toward every other part, the whole drawing inward toward a common doom with no external floor to land on. The collapse is not a fall onto something, but a falling together of everything, the matter of the cosmos, converging on itself from all directions at once. Gravity, pulling not down but inward, everywhere, toward a center that is not a place so much as the mutual destination of all things. It is a fall with no bottom, except the crushing together of the universe with itself, and that makes it stranger and more total than any ordinary fall could ever be. Think again about the ball thrown upward into the sky. As it rises, gravity slows it. If you throw it gently, it slows, stops, and falls back down. If you could throw it hard enough, faster than a certain critical speed, it would slow, but never quite stop, escaping the Earth's gravity entirely, and coasting off into space forever. The dividing line between these two fates is a particular speed, the escape velocity, and which side of that line you are on determines everything: fall back or fly free. The expanding universe faces an almost identical choice, governed by an almost identical balance, but on the grandest possible scale, with the fate of all existence hanging on the outcome. In the universe's case, the outward rush is the expansion, the swelling of space carrying the galaxies apart. The inward pull is gravity, the collective attraction of all the matter in the cosmos, every galaxy tugging on every other, the whole vast assembly of matter pulling inward, trying to halt the expansion and draw everything back together. And just as with the ball, there are two possible outcomes, divided by a critical line. If there is enough matter in the universe, enough mass to generate enough gravity, then gravity will win. The expansion will slow and eventually halt and then reverse, and everything will come falling back together. That is the big crunch. But if there is not enough matter, if gravity is too weak to overcome the expansion, then the universe will expand forever. The galaxies coasting apart for all eternity, the cosmos growing ever larger, colder and emptier, without end. The deciding factor in this classic picture is the density of the universe. How much matter is packed into each region of space? Cosmologists defined a special value called the critical density, the exact dividing line between the two fates. If the average density of the universe is greater than this critical value, there is enough matter, enough gravity, to eventually reverse the expansion and bring on the big crunch. If the density is less than the critical value, gravity loses and the universe expands forever. And if the density is exactly equal to the critical value, the universe sits perfectly balanced on the knife's edge, expanding forever, but ever more slowly, never quite collapsing, but never quite escaping either. For much of the 20th century, this was the central question of cosmology. Which side of the critical density is our universe on? Is there enough matter to bring everything crashing back, or will the cosmos drift apart forever? There is an elegant and surprising way that this question connects to the very shape of the universe, to the geometry of space itself, and it is worth a brief look because it deepens the picture. According to our best theory of gravity, matter does not just pull on other matter. It actually curves the space around it, bends the geometry of the cosmos, and the total amount of matter in the universe, the same thing that determines whether gravity can reverse the expansion, also determines the overall shape of space on the largest scales. If the density is above the critical value, enough to eventually cause collapse, then space curves around on itself in a particular way, closing up like the surface of a vast sphere, a finite universe that folds back on itself. If the density is below critical, space curves the opposite way, opening out like an endless saddle, an infinite universe that expands forever. and if the density sits exactly at the critical value, space is flat, balanced precisely between the two, extending without curving, expanding forever, but only barely. So the fate of the universe and the shape of the universe are, in this classic picture, two faces of the same question, both determined by how much matter the cosmos contains. A universe destined for the Big Crunch would be a closed, finite, sphere-like universe, curving back on itself, holding enough matter for gravity to eventually win. A universe destined to expand forever would be open or flat, infinite, gravity too weak to ever reverse the outward rush. To ask whether the universe will collapse is, in this sense, to ask what shape it has. Whether it is closed and finite or open and endless, the destiny and the geometry bears bound together by the single quantity of cosmic density. It is a beautiful unification of two of the deepest questions one could ask about the cosmos, its shape and its fate, revealed to be the same question, wearing two different faces. This question is not merely academic, because the two fates could not be more different, and they represent two utterly opposed visions of how everything ends. In one, the universe expands forever, slowly running down into a cold, dark, empty eternity. The galaxies drifting beyond each other's reach, the stars eventually burning out, the cosmos fading into a vast, frozen, lifeless darkness. In the other, the Big Crunch, the universe reverses and collapses, ending not in cold and emptiness, but in heat and density and violence. Everything crushed back together in a searing finale. Cold death or fiery collapse, endless expansion or total reversal, the whisper of an eternal fade or the roar of a final crush. It is worth sitting with how completely opposite these two destinies are, because they represent not just different outcomes, but different kinds of ending, almost different moods of finality. The endless expansion is an ending of dispersal, of dilution, of everything spreading so far apart that the universe becomes effectively empty, each galaxy isolated, beyond the reach of any other, the stars burning out, one by one, the cosmos sinking into a cold, dark, silent, infinitely thin eternity. It is an ending of cold and slow fading, of things drifting beyond one another forever. The Big Crunch is the precise opposite, an ending of gathering, of concentration, of everything rushing back together into a single searing point. The universe not emptier but more crowded, not colder but hotter, not darker but blindingly bright, until all of it is crushed together in a finale of heat and density and violence. One ending scatters, the other gathers. One freezes, the other burns. One fades to nothing across infinite time. The other slams shut in a final crush. For a being trying to imagine the fate of the universe, these two possibilities could hardly be more different in character, and yet for most of the 20th century, we genuinely could not say which one awaited us. The universe held its fate close, the answer hidden in quantities we had not yet measured, the density of matter, the behavior of the expansion, and later the nature of dark energy. We knew the cosmos must face one of these destinies, the long cold fade or the fiery crush, but we could not yet tell which, and the question hung over cosmology as one of the deepest and most haunting open problems there was. The Big Crunch was one of the two great answers. The fiery one, the one in which the universe ends not with a whimper but with a roar. For decades, cosmologists could not say with certainty which fate awaited the universe. and the Big Crunch stood as one of the two great possibilities, a genuine candidate for the end of all things, the scenario in which gravity wins and the cosmos comes crashing home. And to truly grasp it, we have to imagine the moment it all turns around, the moment the great expansion stops and begins to run backward. Picture the universe in the scenario where gravity is destined to win. For billions upon billions of years, it expands just as it does now, the galaxies drifting apart, the cosmos growing ever larger. But the expansion is slowing. Gravity, patient and relentless, is applying its inward pull across the entire universe, draining momentum from the expansion, the way gravity drains the upward speed from a rising ball. For ages, this slowing is almost imperceptible. The universe keeps growing, just a little less quickly, with each passing eon. The galaxies keep receding, but their flight is gradually losing its energy. The great outward rush, running down by infinitesimal degrees over spans of time that dwarf the current age of the cosmos. And then at last, after an almost inconceivable stretch of time, the universe reaches its largest size. The moment of maximum expansion, the turning point. The expansion, slowed to nothing by gravity's endless pull, finally halts. For one strange instant, the universe is neither growing nor shrinking, perfectly poised at its greatest extent. The galaxies momentarily at rest relative to the great expansion, the cosmos holding its breath at the very peak of its growth. This is the turnaround, the pivot of the entire history of the universe, the hinge between the age of expansion and the age of collapse. Everything before it has been growth. Everything after it will be collapse. It is the high point of all existence, the maximum reach of the cosmos, and it lasts only a moment before gravity, having stopped the expansion, begins to do something far more frightening, to reverse it. It is worth dwelling on how delicate and precise this turning point would be, because it reveals the true nature of the balance the universe is poised upon. For the expansion to halt exactly, for the outward rush to slow precisely to zero, requires a perfect equilibrium between the momentum of the expansion and the inward pull of gravity, reached at one exact moment after billions of years of slowing. Before that moment, the universe is still, however slightly, growing. After it, the universe is, however slightly, shrinking. The turnaround is the infinitely thin dividing line between the two, the single instant when growth becomes collapse, an event of cosmic significance that would pass in a moment and could only be recognized, even in principle, by noticing that the expansion which had defined all of history had quietly given way to its opposite. The grandest pivot imaginable, the hinge of the entire cosmic story, would be a moment of perfect, silent balance, the universe poised for an instant at its greatest extent, before beginning the long fall home. And there is something poignant in the thought of that maximum moment, the universe at its largest, its most spread out, its coolest and most spacious. The farthest the galaxies would ever drift from one another, the greatest the cosmos would ever be. Everything after that peak would be diminishment, contraction, the slow, then rapid undoing of the great expansion. The turnaround would mark not just a change of direction, but the absolute zenith of the universe's growth, the high water mark of all cosmic history, the moment beyond which the cosmos would only ever grow smaller. It is a strange thing to contemplate, the largest the universe will ever be, a single moment at the very top of its long arc, after which the only direction left is down, inward, together toward the crush. For after the turnaround, gravity does not simply hold the universe steady. It keeps pulling, and now, with nothing to oppose it, that inward pull begins to draw everything back together. Slowly at first, then faster. The galaxies that had spent eons drifting apart begin to drift back toward one another. The expansion of space reverses and becomes a contraction. Space itself, which had been stretching for billions of years, begins to shrink. And the great cosmic rush, which had been carrying everything outward since the beginning, turns around and begins to carry everything inward. The universe starting the long fall back toward the dense, hot state from which it came. The collapse has begun, and there would be a way to see it, a visible sign written across the sky, if anyone were there to look. Remember that the expanding universe reveals itself through the redshift of distant galaxies, their light stretched toward the red as they recede. In a contracting universe, this would reverse. The galaxies, now approaching, rather than receding, would show the opposite effect. Their light shifted toward the blue, compressed rather than stretched, the signature of objects rushing toward you rather than away. The sky would carry the mark of the reversal, the ancient redshift giving way to a universal blue shift. Every distant galaxy now bearing the telltale blue tint of approach. The universe would announce its own collapse in the color of its light, the great cosmic signal flipping from the red of expansion to the blue of contraction, a sky-wide herald of the falling together to come. This flip from red to blue is more than a technical detail. It would be the single clearest sign written across the entire heavens that the fate of the universe had turned. For the whole of cosmic history, up to the turnaround, any observer studying distant galaxies would have found their light stretched toward the red, the universal signature of a cosmos expanding, the same redshift that first revealed the expansion to us. After the turnaround, that signature would gradually, inexorably reverse. Galaxy by galaxy, the redshift would diminish, fade, and then cross over into blue shift, the light now compressed rather than stretched, the mark of approach rather than recession. An observer watching over the immense ages of the reversal would witness the entire sky slowly change its character, the ancient red of expansion giving way everywhere to the blue of contraction, the whole universe announcing, in the shifted color of its every distant light, that the long expansion had ended and the great collapse had begun. It is a strange and haunting image, a sky in which every distant galaxy bears the blue tint of approach, a cosmos visibly falling inward, its light compressed by the contraction of the very space it travels through, where our sky tells a story of things receding, fading, drifting away into ever greater distance and ever deeper red. That future sky would tell the opposite story, of things returning, approaching, drawing nearer and bluer, the cosmos closing in. The color of the light would be the readout of the universe's fate, and in the era of collapse, that readout would shine blue across the entire sky, a constant, universal sign that everything was falling back together, that the long road to the crushing finale had been entered upon at last. And from that point on, the universe would be running in reverse, retracing its expansion backward, falling inward toward a finale that would build, over the ages, from a gentle drift to a violent, crushing, all-consuming collapse. There is something profoundly strange about the very idea of the turnaround, the single moment when the largest possible thing, the entire universe, stops growing and begins to shrink, and it rewards a moment's contemplation for the whole of cosmic history up to that point. Expansion would have been simply the way things are, as fundamental and unquestioned as the passage of time. The universe always larger today than yesterday. The galaxies always a little farther apart than before. To anyone living in such a universe, expansion would seem like an eternal truth, a permanent feature of reality. And then at the turnaround, that eternal truth would quietly end. The growth would cease, and the very next moment, the universe would begin to do something it had never done in all its history: to grow smaller. It would be the reversal of the most basic trend in all of existence, the flipping of a direction that had held since the beginning, the universe crossing from a history of growth into a future of collapse at a single, silent, pivotal instant. And the strangeness deepens when you consider that this turning point would pass without any sudden drama, without any cosmic alarm. There would be no explosion of the turnaround, no violent event, marking the moment, just the expansion slowing to nothing, and then imperceptibly reversing. The collapse would begin so gently that, at first, almost nothing would seem different. The galaxies would still be far apart. The sky would still look much as it had. Only very slowly, over spans of time that beggar the imagination, would the reversal make itself felt, the distances beginning to shrink, the blue shift creeping into the light, the universe gathering itself for the long fall home, the most momentous turning point in the entire history of the cosmos would arrive, not with a bang but with a silence, a quiet pivot from growth to collapse that would take ages to reveal its true and terrible consequences. In the early stages of the collapse, the change would be slow and almost gentle, mirroring the slow beginning of the reversal. The galaxies would drift back toward one another over enormous spans of time, the contraction of space gradually gathering pace, the universe shrinking by degrees so gradual that for a long while, little would seem to change. But the contraction would feed on itself. As the universe grew smaller, the galaxies would draw closer. And as they drew closer, gravity's grip would tighten, accelerating the collapse. What began as a gentle drift inward would build over the eons into a faster and faster falling together, the universe contracting at an ever-increasing rate. The great collapse gaining momentum as it went, exactly as a falling object accelerates the farther it falls. And as the universe contracted, something profound would happen to its temperature. Recall that the early universe was hot and dense, and that it has been cooling for billions of years as it expanded. The heat of its beginning diluted and stretched out across ever-growing space. A contracting universe would reverse this, too. As space shrank and everything was forced closer together, the energy of the cosmos would be compressed back into a smaller and smaller volume, and the temperature would begin to climb. The faint, cold afterglow of the early universe, the radiation that fills all of space and that has cooled over billions of years to just a few degrees above the coldest possible temperature, would begin to warm again as it was compressed. The universe, which had spent its whole history history growing colder, would start to grow warmer. The ancient chill reversing, the cosmos heating up as it fell inward, the long cooling of all of time running backward. There is something almost vertiginous in imagining the temperature of the entire universe beginning to rise after billions of years of falling, because it would mean the reversal of one of the most fundamental trends in all of cosmic history. The universe has been cooling for its entire existence. The faint background radiation that fills all of space, the leftover warmth of the early cosmos, has been dropping in temperature for billions of years as the expansion stretched and diluted it. Until today, it sits at just a few degrees above the coldest temperature physically possible, a deep and pervasive cold, filling all the spaces between the stars. A collapsing universe would take that ancient, deepening cold and reverse it, the background radiation warming again as the contraction squeezed it, the temperature of the whole cosmos beginning a long climb back toward the heat of its origins. The very coldness of deep space, which has been growing for the entire age of the universe, would begin to undo itself, the cosmos warming everywhere at once as it fell. At first, this warming would be utterly imperceptible, the temperature rising by amounts too small to matter, the universe still overwhelmingly cold and dark and spacious. For an immense span of the collapse, you could live in such a universe as never notice that the ancient cooling had reversed, that the cosmos had begun, ever so slightly, to warm. But the trend, once begun, would be relentless, and it would accelerate along with the collapse, the warming gathering pace as the contraction did, slow and gentle for ages, and then climbing faster and faster as the universe shrank toward its finale. The reversal of the cosmic chill would be one of the surest signs of the collapse. A universe that had been growing colder since the beginning, now, against all the habit of its history, beginning inexorably to heat. For a vast stretch of the collapse, this warming would still be gradual. The universe shrinking and heating by slow degrees, the galaxies approaching but still separated by great distances. But the process would be relentless and accelerating. The sky, instead of growing emptier and darker as it does in an expanding universe, would slowly begin to grow more crowded and more bright. Galaxies that had drifted to enormous distances would creep back into view, their light blue shifted, their numbers increasing as the shrinking universe packed them closer together. The cosmos would become a more and more crowded place, the galaxies converging, the spaces between them closing, the universe filling up with approaching light as everything fell back toward everything else. And there would come a point, deep in the collapse, when the galaxies, drawn relentlessly together by the contraction, would begin to crowd so closely that they could no longer remain separate. The vast distances that had kept them apart would shrink away, and the galaxies would start to merge, to overlap, to crash into one another. The great islands of stars that had drifted alone for so long now forced together by the shrinking of space itself. There is a strange grandeur and horror in imagining this stage, when the galaxies themselves, those vast cities of billions of stars that have stood as the great solitary structures of the cosmos, would lose their isolation and begin to collide. For the whole of cosmic history, galaxies have been mostly separate, vast distances of empty space holding them apart. Each one, a remote island, sailing alone through the dark. Collisions between galaxies do happen even now, but rarely, special events scattered across cosmic time. In the deep collapse, such collisions would become the norm, then constant, then total, as the shrinking of space forced galaxy into galaxy. Everywhere at once, the great islands ceasing to be separate at all, merging into a single crowded mass of stars filling the contracting cosmos. The grand architecture of the universe, built over billions of years, the delicate arrangement of galaxies stretching across space in their vast cosmic web would dissolve into a uniform, crowded, heating sea, the distinctions between the great structures erased by the relentless squeezing of space, and the stars themselves, within that crowded mass, would not long survive the gathering heat and density. As the collapse drove the temperature ever higher and packed the matter ever closer, the stars would be overwhelmed, their light lost in the rising universal glare, their substance merging into the general searing soup of the contracting cosmos. The familiar objects of the universe, the galaxies and then the stars, would be unmade in turn, dissolved into the hot, dense mass of the collapse, the cosmos shedding its structure layer by layer as it fell, until nothing recognizable remained, only the gathering, heating, crushing convergence of all things toward the finale. The structure of the universe, the grand arrangement of separate galaxies scattered across the cosmos, would begin to break down, dissolving as everything was compressed into an ever smaller volume. The cosmos would be losing its familiar form, the separateness of things, collapsing along with the space that had held them apart, all of it merging, crowding, heating, falling together toward the searing finale that lay ahead. It is worth dwelling on the eerie quality of a universe running its history in reverse, because there is something almost uncanny in it. Everything that took the universe billions of years to build, in the long age of expansion and cooling, would be unbuilt, undone, in the collapse, but in the opposite order. The universe base spent ages cooling enough for atoms to form, then more ages for stars to ignite, then more for galaxies to assemble and drift into their grand arrangement across the cosmos. The collapse would dismantle all of this, but running backward, the grand structure coming apart, first as galaxies were forced together, then the stars themselves overwhelmed, then, as the heat climbed, the atoms broken, the whole patient construction of cosmic history disassembled in reverse, the universe retracing its own past toward the hot, dense state it had so long ago left behind. It would be as if the entire film of cosmic evolution, billions of years long, were played backward. Every step of the universe's building undone in turn, the cosmos unmaking itself on the way down. And there is a particular strangeness in imagining the sky. During this reversal, the way the heavens themselves would testify to the collapse. For the whole of an expanding universe's history, the sky grows emptier and darker, galaxies receding into ever greater distances, the night deepening as the cosmos spreads out. A collapsing universe would reverse this trend utterly. The sky would grow brighter, more crowded, more filled, night after cosmic night. As the shrinking of space packed more and more light into view, the darkness between the stars would slowly fill in. The heavens would grow busier and more luminous as the collapse proceeded, the very emptiness of space being squeezed away, until eventually there would be no darkness left at all. Only the gathering, brightening, heating glare of a universe falling back together. The sky itself would chronicle the collapse, its deepening brightness, a visible measure of the cosmos closing in. As the collapse entered its final stages, the universe would become a place of almost unimaginable violence and heat, and the gentle drift of the early contraction would give way to a furious, headlong rush toward the end. The galaxies, having merged and crowded together, would themselves be torn apart, their stars scattered and crushed into a single seething mass, as the universe shrank toward a fraction of its former size. The temperature, which had been climbing slowly for so long, would now begin to soar, the compression so extreme that the entire cosmos would heat up toward the conditions of its fiery beginning, the long-cooled radiation of space blazing back to life as it was squeezed into an ever tinier volume. The sky, in these final stages, would no longer be dark. It would blaze. As the universe contracted and heated, every direction would fill with searing light, the compressed radiation of the entire cosmos, glowing brighter and hotter with each passing moment, until the whole sky became an inferno, a blinding, all-enveloping brilliance with no dark spaces left between the stars, no gaps, no emptiness. Only the universal glare of a universe crushed almost back to its origins. The cold, dark, spacious night sky we know would have become its opposite, a searing, brilliant, all-consuming furnace. The light of everything compressed together, the cosmos transformed into a single blazing cauldron of heat and radiation. There is a terrible irony in this, that a universe which spends its entire ordinary history in darkness, the night sky black and deep with only scattered points of light, would end not in deeper darkness, but in blinding, universal brightness. We tend to associate endings with fading, with dimming, with things going dark, and the other possible fate of the cosmos, the endless expansion, does end that way, in cold and dark and emptiness. But the Big Crunch ends in the opposite, in a brilliance so total that there is no darkness left anywhere. Every direction ablaze, the whole sky a single uniform glare of compressed light and heat. It would be an ending of too much light rather than too little, of unbearable brightness rather than encroaching dark. The cosmos going out, not like a dying ember, but like a furnace, stoked beyond all limit, brighter and brighter, until the very concept of a dark sky had become impossible. And there would be no escaping it, nowhere to hide from the rising heat and light, because it would not be coming from any one direction, but from everywhere at once, from the very space itself as it compressed. In an exploding star, the heat radiates outward from a center, and there is an outside to flee toward. But the heat of the collapsing universe would fill all of space uniformly. With no center and no outside, the entire cosmos becoming the furnace, every point heating along with every other, the glare and the warmth pressing in from all directions simultaneously. There would be no cool refuge, no dark corner, no outside to escape to. Only the universal, omnipresent, ever-climbing heat of a universe crushing itself toward its finale, filling every last region of shrinking space with the same searing brilliance. And the heat would keep climbing, and as it did, it would begin to undo the very structure of matter. Recall that in the hot early universe, It was too hot for atoms to hold together. Only as the universe cooled and expanded did matter settle into the stable atoms we know. The collapse would reverse this. As the temperature soared, the heat would become so intense that atoms could no longer survive, their electrons torn away, matter reduced to a searing plasma. And as the compression continued and the temperature climbed still higher, even the nuclei at the hearts of atoms would be broken apart, the building blocks of matter, dismantled by the rising heat. The cosmos reverting to a state of pure, hot, dense energy and fundamental particles, the entire history of matter, from the first atoms to the last, running backward in the crushing furnace of the collapse. There is a grim poetry in the order of this unmaking, because it would precisely reverse the order in which matter was built. In the early universe, as it cooled, the most basic particles first came together to form the simplest atomic nuclei, and only much later, as things cooled further, did electrons join those nuclei to make complete atoms, and only far later still did atoms gather into stars where heavier elements were forged. The collapse would undo all of this in reverse sequence. First, the complex structures and the heavy elements forged in stars would be destroyed as the stars themselves were torn apart and the heat climbed. Then, as the temperature rose further, the atoms would lose their electrons, reverting to bare nuclei in a searing plasma. And then, at the highest temperatures, even those nuclei would be broken apart into their most basic constituents, the universe, dismantling matter all the way back down to the elementary particles from which it had first been assembled. The entire architecture of matter, built up step by step over the cooling ages, would be demolished step by step in the heating collapse. In exact reverse order, the cosmos retracing the construction of matter backward toward its raw beginnings. And the pace of all this would be accelerating ferociously. The collapse, like a fall, would move faster the further it progressed, so that while the early contraction took ages upon ages, the final stages would rush past with terrible speed, the universe shrinking and heating faster and faster as it approached the end. The last great structures destroyed in what would be, by comparison to the eons that came before, the merest flicker of time. The collapse would not be a steady, measured affair throughout. It would be a gathering avalanche, slow and almost imperceptible at first, then quickening, then plunging headlong, the universe rushing toward its finale at an ever-mounting rate. The final unmaking compressed into a span vanishingly brief against the immense, slow ages of the contraction's beginning. The end, when it came, would come fast. In the very final moments, the universe would be approaching a state almost beyond description. All the matter and energy of the entire cosmos compressed into a smaller and smaller volume, the temperature and density climbing toward unimaginable extremes. Everything that had ever existed crushed together into a searing, dense, violent finale. The black holes scattered throughout the universe, themselves the densest objects the cosmos can make, would merge into one another and into the surrounding mass, swallowed up in the general collapse. Every structure, every distinction, every separate thing would be erased in the crush. The cosmos converging toward a single point of inconceivable density and heat, the mirror image of the hot, dense state from which the expansion began. all of existence falling together into one final, crushing instant. This is the Big Crunch in full. Not a fading, not a gentle running down, but a violent, total, accelerating collapse. The universe slamming shut, everything crushed back together in a finale of heat and density beyond anything that has existed since the very beginning. And what happens at that final point, the very end of the collapse, is one of the deepest and most honest mysteries in all of physics. Here, we must be honest, because honesty is what separates real science from speculation dressed up as fact. And the truth is that we do not know what happens at the very end of a big crunch. As the universe is crushed toward that final state of extreme density and temperature, our physics begins to falter. The theories that describe the cosmos so beautifully across its ordinary history, the physics of gravity on the largest scales and the physics of particles on the smallest, both of which work superbly in their own domains, come into conflict in conditions this extreme, where enormous mass is crushed into a vanishing volume. In that regime, we would need a complete theory uniting gravity and the quantum world, a theory we do not yet have to say what truly happens. And so, at the final point of the collapse, our equations stop giving clear answers. We can describe the universe falling inward, heating, crushing, right up to the edge of that final state. But the final state itself lies beyond the reach of our current understanding. This is not a failure of the idea. It is a frontier of knowledge, and it is important to sit with it, honestly, rather than papering over it with confident-sounding stories. Some have speculated about what the final crush might lead to, but these are speculations, not established science, and many of them venture into territory where physics simply cannot yet follow. The careful, honest position is to say that the collapse would carry the universe toward a state of extreme density and heat that our current theories cannot fully describe, and that what happens at that ultimate point is, for now, genuinely unknown. We have reached, in imagining the Big Crunch, all the way to the limits of what we can currently say about the fate of everything. And at those limits, the honest answer is that the final moment is a mystery our physics is not yet equipped to resolve. It is worth understanding why our theories break down there, specifically, because it points to one of the great unfinished tasks of physics. We have two magnificent theories of the physical world. One describes gravity and the behavior of space and time on large scales, and it works superbly for planets, stars, galaxies, and the expanding universe as a whole. The other describes the quantum world of particles on the smallest scales, and it works superbly there. For almost all of cosmic history, these two theories never seriously conflict, because gravity dominates the large, and the quantum world dominates the small, and the two rarely have to be applied to the same thing at once. But in the final crush of a big crunch, all the mass of the universe would be compressed into a tiny volume, which means that gravity, the physics of the very large, and the quantum world, the physics of the very small, would both be in full force at the same place and the same time. And there the two theories give contradictory, nonsensical answers. To describe that final state, we would need a single theory that unites gravity and the quantum world, a theory of quantum gravity. And despite enormous effort, we do not yet have a complete and proven one. So the breakdown at the end of the Big Crunch is not a vague hand wave, or a failure of imagination. It is a precise and well-understood gap in our knowledge. The same gap that appears whenever matter is crushed to extremes, the missing theory of quantum gravity that physicists have sought for generations. The final instant of a collapsing universe is one of the places where that missing theory would be needed. And until we have it, the honest answer about what happens there is that we cannot yet say. This is not a comfortable answer, and it is not a dramatic one, but it is the true one. And there is integrity in stating it plainly, rather than dressing the gap in confident-sounding speculation. The end of the Big Crunch sits behind the same veil that hides the deepest workings of crushed matter everywhere, awaiting a theory we have not yet completed. There is something fitting, even humbling, in this, that the ultimate fate of the universe, if it ends in collapse, would carry it into conditions so extreme that our finest theories fall silent. It is a reminder that our understanding, vast and powerful as it is, has edges, that there are regimes of reality so far beyond ordinary experience that we have not yet found the tools to describe them. The Big Crunch, in its final instant, takes us to one of those edges, the point where the crushing together of all things exceeds what we can currently comprehend. And rather than fill that gap with invented certainty, the honest scientist holds it open, acknowledging that the deepest question, what happens at the very end of a collapsing universe, remains, for now, unanswered, a frontier still waiting to be reached by some future understanding we do not yet possess. This honesty is not a weakness of the Big Crunch as an idea. It is a mark of its scientific seriousness. A myth would tell you exactly what happens at the end, would fill in every detail with confident certainty, because a myth answers to the desire for a complete story rather than to the evidence. Science does the harder and more honest thing. It follows the physics as far as the physics can go, and then it stops and says plainly, here is the edge of what we know. The Big Crunch can be described in remarkable detail across almost the entire collapse. The turnaround, the contraction, the heating, the destruction of structure, the dismantling of matter, all of it grounded in physics we understand well. And then, at the very last instant, where the conditions exceed what our theories can handle, the honest description stops. That stopping point is not a flaw in the story. It is the story being told with integrity, marking clearly the boundary between what we know and what we do not. And there is something almost fitting in the fact that the ultimate fate of everything should end for us in a question mark rather than a period. The universe keeps its deepest secret to the last, the final instant of a possible collapse, lying just beyond our reach, awaiting a theory of quantum gravity we have not yet completed. Perhaps one day we will have that theory, and will be able to follow the collapse all the way to its conclusion and say what truly happens at the end. For now, we can say only that the universe would fall toward a state of extreme density and heat that our physics cannot fully describe, and that what lies at the very bottom of that fall is, honestly and genuinely, unknown. It is a humble place to end the story, but it is the true place, and there is a kind of dignity in ending it there, rather than pretending to a certainty we do not have. So the picture of the Big Crunch, traced honestly, is this: a universe that expands for ages, slows under gravity's pull, halts at a moment of maximum size, and then reverses, collapsing back together with gathering speed, heating and crushing as it falls, the galaxies merging, the structures destroyed, the matter dismantled, the sky ablaze, everything converging toward a final state of extreme density and heat that lies beyond our current physics to describe. It is a vision of an end that is violent rather than gentle, hot rather than cold, a crushing together rather than a drifting apart. And for much of the history of cosmology, it stood as one of the two great candidate fates for the universe. But then, near the end of the 20th century, a discovery arrived that seemed to change everything, and that pushed the big crunch, for a time, to the margins. For most of the 20th century, cosmologists assumed that the expansion of the universe must be slowing down. It seemed obvious. Gravity pulls inward, and so the expansion, like a thrown ball, should be losing speed, decelerating, the only question being whether it would slow enough to eventually reverse into a big crunch, or merely coast apart forever. The whole debate was about how fast the expansion was slowing. So, in the late 1990s, two teams of astronomers set out to measure that slowing precisely by observing a particular kind of stellar explosion in distant galaxies, explosions so consistent in their brightness that they could serve as cosmic mile markers, letting astronomers gauge distances across the universe and measure how the expansion had changed over cosmic time. What they found astonished them and overturned the assumption that had stood for generations. The expansion of the universe was not slowing down at all. It was speeding up. The galaxies were not merely coasting apart. They were flying apart, faster and faster, the expansion accelerating, as though some mysterious force were pushing the universe outward, working against gravity, driving the cosmos to expand at an ever-increasing rate. This was the opposite of what everyone had expected. Gravity should have been slowing the expansion, but something was overpowering gravity on the largest scales, accelerating the growth of the universe, pushing everything apart with mounting speed. The way this was discovered is itself a remarkable story, worth pausing on, because it shows how a careful measurement can overturn a deep assumption. The astronomers were studying a particular kind of exploding star, a stellar detonation that always reaches very nearly the same true brightness wherever it occurs. Because these explosions are so consistent, they make superb cosmic distance markers. By comparing how bright such an explosion truly is with how bright it appears from Earth, astronomers can calculate how far away it is. And by studying the stretching of its light, they can tell how fast the universe was expanding when that light set out. By gathering many of these explosions at many different distances, the teams could effectively measure the expansion of the universe at different points in its history, reconstructing how the expansion rate had changed over billions of years. They expected to find that the expansion had been faster in the past and was slowing down, decelerating under gravity, as everyone assumed it must. Instead, the distant explosions were fainter than expected, which meant they were farther away than a decelerating universe would place them, which meant the expansion had not been slowing down, but speeding up. The teams checked and rechecked, looked for every possible error, scrutinized their assumptions because the result was so unexpected that it demanded the harshest skepticism. But the conclusion held. Both teams, working independently arrived at the same astonishing answer. The expansion of the universe is accelerating. It was one of those rare moments when a careful measurement does not merely refine what we know but overturns it, replacing a deep and long-held assumption with its opposite. The universe was not coasting to a stop under gravity's pull. It was being driven apart, faster and faster, by something no one had expected and no one understood. This discovery pointed to the existence of something cosmologists came to call dark energy, a mysterious form of energy filling all of space, exerting a kind of outward pressure, a repulsive influence that opposes gravity and drives the accelerating expansion. The nature of this dark energy remains one of the deepest mysteries in all of science. We do not know what it is, only that it appears to make up the majority of the universe, and that it is pushing the cosmos apart at an ever faster rate. It is worth letting the strangeness of dark energy register, because it is one of the most astonishing and least understood facts in all of science. The matter we can see, all the stars and galaxies and glowing gas, the ordinary material that makes up everything familiar, turns out to be only a small fraction of the contents of the universe. A larger portion is invisible dark matter, whose gravity helps hold galaxies together. And larger still, making up the majority of the entire cosmos, is this dark energy, this mysterious something that fills all of space and pushes it apart, and about which we know almost nothing except its effect, the dominant component of the universe. The thing that will largely determine its fate is something we cannot see, cannot directly detect, and cannot yet explain. We have given it a name, but a name is not an understanding. We are in the strange position of knowing that the majority of reality is made of something whose nature is a complete mystery to us. And because dark energy dominates the universe and drives its expansion, the question of the cosmos's fate becomes, in large part, the question of what dark energy actually is. If we understood its true nature, we could predict whether the universe will expand forever or someday collapse. But we do not understand it, and so the fate of everything hangs on this open question. This mysterious majority component, whose behavior we are only beginning to probe. It is humbling and somehow fitting that the destiny of the entire universe should depend on the thing we understand least, that the answer to the grandest question of all should be locked inside the deepest mystery in cosmology. But its discovery had an immediate and dramatic consequence for the question of the universe's fate. If the expansion is not slowing but accelerating, driven by a dark energy that pushes everything apart, then gravity is not winning the cosmic tug-of-war. It is losing, and a universe whose expansion is accelerating is not headed for a big crunch at all. It is headed for endless expansion, growing forever, faster and faster, the galaxies flying apart for all eternity. For a while, this reversal of fortune for the big crunch felt almost complete. The discovery of acceleration was so solid, so well confirmed, that the long, cold expansion came to seem all but certain, and the fiery collapse receded into the background, a fate the universe had apparently considered and declined, a possibility that seemed to belong to the history of cosmology rather than to its future, a closed chapter rather than an open question, settled and set aside. But as we will see, certainty was never quite warranted, because it rested entirely on one unproven assumption about the mysterious dark energy driving the acceleration, an assumption that recent science has begun, quietly but seriously, to question. And so, with the discovery of the accelerating expansion, the Big Crunch fell out of favor. If dark energy is a permanent, unchanging feature of space, an eternal outward pressure that never weakens, then the universe will simply expand forever, accelerating without end, drifting toward the cold, dark, empty fate, rather than the fiery collapse. The galaxies would recede beyond one another's reach, the cosmos growing ever more dilute and lonely, the stars eventually burning out, everything fading into a frozen, scattered darkness across an eternity of expansion. This, not the Big Crunch, became the favored picture of the universe's fate. Not a violent collapse, but an endless, accelerating dispersal, a slow fade into cold and dark, rather than a crushing slam into heat and density. For a time it seemed the Big Crunch had been ruled out, a dramatic fate that the universe had apparently declined to pursue. But the story does not end there, because the key to the whole question, the nature of dark energy itself, remains unknown, and that uncertainty has quietly reopened the door. Here is the crucial uncertainty at the heart of the matter. We do not know what dark energy actually is. We know it is there. We know it is driving the accelerating expansion. But its true nature is one of the great open questions of physics, and the fate of the universe depends entirely on the answer. If dark energy is what is called a cosmological constant, a fixed, unchanging energy of space itself, eternal and constant in strength, then yes, the universe will expand forever, accelerating without end, and the Big Crunch is ruled out. But that is only one possibility. Dark energy might not be constant at all. It might be a dynamic thing, something that changes over time, that has been one strength in the past and could be another in the future. And if dark energy can change, then the door to a Big Crunch swings open again. Consider what would happen if dark energy, rather than being a fixed feature of space, were something that could weaken over time, or even reverse. Right now, dark energy pushes outward, driving the acceleration. But if it were to fade, to lose its strength, then its outward push would diminish, and gravity, the inward pull of all the matter in the cosmos, could once again become the dominant influence. And if dark energy were not merely to weaken but to flip, to become attractive rather than repulsive, pulling inward instead of pushing outward, then it would join forces with gravity, and the combined inward pull could halt the expansion and drive the universe into collapse. In such a scenario, the accelerating expansion we see today would be only a phase, a temporary chapter, destined to give way to a slowing, a halting, and finally a reversal. The cosmos turning around and falling back together into a Big Crunch after all. The very dark energy that seemed to rule out the collapse could, if it behaves in these ways, be the thing that eventually brings it on. To see how this could work, it helps to think of dark energy not as a fixed quantity, but as something that might have its own behavior over time, like a field spread through space whose strength can evolve. In many serious theoretical models, dark energy is exactly this kind of dynamic entity, sometimes called by names that refer to its changing character. And in these models, its strength is not fixed but set by the state of an underlying field that can shift as the universe ages. Such a field could grow weaker over cosmic time, easing its outward push. It could settle towards zero, removing the acceleration. Or, in some models, it could pass through zero and become negative, so that what was once a repulsive push becomes an inward pull, adding to gravity, rather than opposing it. In any of the scenarios where dark energy weakens enough or reverses, the long-term fate of the universe flips from endless expansion back toward eventual collapse. The accelerating expansion we observe today would then be revealed as a passing phase, not a permanent condition, and the Big Crunch would be restored as the ultimate destiny, merely postponed rather than cancelled. What makes this more than abstract theorizing is that we have no observational proof that dark energy is constant. We have simply assumed it for simplicity, because a constant is the easiest possibility to work with, and because, until recently, the data could not distinguish a constant dark energy from a slowly changing one. That is beginning to change. Enormous surveys are now mapping the positions and motions of millions upon millions of galaxies across cosmic history, precisely to measure whether dark energy has been constant or has evolved. And some of the early results from these efforts have hinted, tentatively and controversially, that dark energy might indeed be changing, might have been somewhat stronger in the past, and be weakening now. If those hints hold up, and that is a very large if, still under intense scrutiny and far from confirmed, they would point to exactly the kind of dynamic dark energy that could, in the deep future, allow the universe to stop expanding and fall back together. The data are not yet decisive. The debate is active and ongoing. But the mere fact that the question is now being measured, rather than assumed, has brought the Big Crunch back from the margins and onto the table as a possibility worth taking seriously. And this is not idle speculation. There are serious theoretical models in which dark energy is exactly this kind of changing, dynamic thing. Models in which the universe is destined to collapse in the future. Some of them even suggesting that a collapse could begin in what is, by cosmic standards, not the impossibly distant future. And remarkably, in recent years, large surveys mapping the dark energy across the cosmos have produced tentative, much debated hints that dark energy might not be perfectly constant after all, that its strength may have changed over cosmic history. These hints are preliminary, and they are the subject of intense ongoing study and genuine scientific debate. They are not anything close to settled, and they may yet dissolve under closer examination. But they have done something important. They have reopened the question. They have reminded cosmologists that the fate of the universe is not yet decided, that the comfortable assumption of eternal expansion rests on the unproven belief that dark energy is constant, and that if dark energy turns out to be a changing thing, the Big Crunch could return as real possibility for the end of all things. So the honest state of the question today is this: the discovery of the accelerating expansion made eternal expansion the favored fate, and if dark energy is a true constant, the Big Crunch will not happen. But the nature of dark energy remains unknown. There are real theoretical models in which the universe does eventually collapse, and recent observations have produced tentative hints that dark energy may not be constant, keeping the question genuinely open. The Big Crunch is not a fate we can confidently predict, but neither is it one we can confidently rule out. It remains a live possibility, a scenario that hangs on the deepest unsolved mystery in cosmology, the true nature of the dark energy that fills the universe and that holds, in its unknown character, the answer to how everything ends. What is striking about this state of affairs is how it has revived a question that many had considered closed. For a stretch of years after the discovery of the accelerating expansion, the textbooks increasingly treated the matter as settled. Dark energy was a constant. The universe would expand forever, and the Big Crunch was a historical curiosity, an idea that had been entertained and then ruled out. But science is not in the business of treating assumptions as facts. And the assumption that dark energy is constant was always exactly that, an assumption, adopted for simplicity and never directly confirmed. As the tools for probing dark energy have sharpened, that assumption has come under real scrutiny. And the possibility that dark energy evolves, once a fringe consideration, has moved toward the center of active research. The Big Crunch has been quietly restored, not as a certainty, but as a genuine contender, a fate the universe might yet have, depending on what the dark energy turns out to be. This is how science is supposed to work, and it is worth appreciating rather than finding unsettling. A possibility is raised, then seemingly ruled out by a discovery, then reopened as that discovery's assumptions are examined more closely and new data arrive. The fate of the universe is not a fixed dogma handed down once and for all, but a living question, refined and revised as our understanding deepens, open to revival when the evidence warrants. The honest position today is one of genuine uncertainty, held with appropriate humility. The universe might expand forever, or it might someday collapse. And which of these is true depends on the nature of dark energy, a question we are actively investigating and have not yet resolved. The Big Crunch is back on the table, not because anyone has proven it will happen, but because we have remembered that we never proved it would not. Now, it would be easy to let a vision like this settle into pure dread, to dwell on the image of everything we know, being crushed back together in a fiery collapse, the galaxies destroyed, the matter dismantled, the cosmos slamming shut, and there is a genuine awe-tinged solemnity in contemplating the possible end of everything, a weight to the thought that the universe itself might have a finale. But there is another way to hold this, a way that is truer to the actual situation and far more conducive to peace. And it begins with the single most important fact about the Big Crunch, the fact that changes everything about how it should make you feel. It's almost incomprehensible distance in time. If the Big Crunch happens at all, it lies an almost unimaginable span of time in the future, so far ahead that the number nearly loses meaning. The universe has already existed for billions of years, and in the scenarios where it eventually collapses, the turnaround and the crush would come only after many more billions of years, perhaps far more than have already passed, a future so distant that the entire history of the Earth, the whole span of life, the complete story of everything that has ever happened, is the merest flicker by comparison. We are talking about a possible event so remote in time, that the gap between now and then dwarfs the entire age of the cosmos so far. Whatever the ultimate fate of the universe, it is not something that bears on your life, or your descendants' lives, or the lives of countless generations beyond imagining. It is a fact about the deep, deep future, almost inconceivably far from the present moment. And so the Big Crunch, for all its drama, poses no threat whatsoever to you, to anyone you know, or to anything you will ever encounter. It is not a danger looming over your life. It is a possibility about the fate of everything in a future so distant that it is almost a kind of abstraction, a question of cosmic principle rather than personal concern. You can contemplate it with the same untroubled fascination you might bring to any great mystery, because nothing about it touches the world you actually inhabit. The collapse, if it comes, is unfathomably far away in time, and the present moment, your present moment, the life you are living right now, is utterly safe from it, separated from any possible cosmic finale by an ocean of time so vast that the finale might as well not exist at all for any practical bearing it has on you. It is genuinely difficult to grasp how much time we are talking about, and the attempt is itself a kind of awe-inducing exercise. The universe has already existed for many billions of years. The Earth formed billions of years ago. Complex life is a few 100 million years old. Our own species, a few 100,000. The whole of recorded human history fits into a few thousand years. A span so brief that, against the age of the cosmos, it is less than the blink of an eye. And the possible Big Crunch lies not thousands, not millions, but many billions of years in the future, likely a span even longer than the entire age of the universe so far. To reach it, you would have to let the complete history of everything that has ever happened play out. And then again, and then many times over. The gulf of time between this moment and any possible collapse is so enormous that the human mind cannot truly hold it. We can write the numbers, but we cannot feel them, for nothing in our experience prepares us for spans so vast, and that very incomprehensibility is a kind of reassurance, because it places the Big Crunch utterly beyond the horizon of anything that could ever matter to a human life. We worry, naturally, about things that might affect us, or those we love, or the world we live in. But the Big Crunch is so remote in time that it falls entirely outside that circle of concern, as distant from your life as it is possible for anything to be. It is not a slow approaching danger, not a clock ticking down within any meaningful span. It is a feature of a future so far removed that countless ages of cosmic history, far more than have already elapsed, would have to unfold before it arrived. To worry about the Big Crunch would be like a creature that lives for a single day fretting about events billions of years away. The scale simply does not permit it to be a personal concern, and that fact frees us to contemplate it purely as a wonder, with no shadow of dread. Seen this way, the Big Crunch becomes not a source of fear, but an object of pure wonder, a magnificent cat's question to contemplate from the safety of an unimaginable distance. And there is something genuinely thrilling in the very fact that we can ask it at all, that we, small and brief beings on a single planet, have come to understand the universe well enough to seriously investigate how it might end, to weigh the possibilities, to measure the expansion, to probe the nature of dark energy, to reason our way toward the fate of all things. For nearly all of human history, the end of the universe was beyond the reach of thought, a matter for myth at most. And now we can study it with telescopes and mathematics and careful reasoning, turning the ultimate question of cosmic fate into a real scientific inquiry. That reach, that astonishing extension of human understanding, all the way to the possible end of everything, is not a cause for dread. It is one of the proudest achievements of the curious mind and a cause for awe. Consider what is actually involved in this achievement, because it is easy to take for granted and genuinely staggering when examined. To ask how the universe will end, and to answer it scientifically rather than mythologically, we had to first discover that the universe is expanding, which required measuring the motions of galaxies millions of times farther away than the nearest stars. We had to work out the physics that governs that expansion, the interplay of gravity and matter and space itself. We had to measure how the expansion has changed over billions of years by observing explosions in galaxies so distant their light has traveled for ages to reach us. We had to discover dark energy, infer its existence from subtle deviations in that light, and begin to probe whether it is constant or changing by mapping the positions of millions upon millions of galaxies. Every one of these steps is a monumental accomplishment, and together they have lifted the question of cosmic fate out of the realm of speculation and into the realm of measurement. We are slowly and carefully learning how to read the destiny of the universe from the light of distant galaxies, and we are not finished. The question of whether the universe will expand forever or someday collapse is, right now, an active area of research with new telescopes and surveys gathering data, precisely to pin down the nature of dark energy, and, with it, the fate of everything. We are living through the chapter of history in which this question is being seriously attacked, perhaps even answered, our generation among the first, with the tools to genuinely investigate how the cosmos will end. There is something thrilling in that, in being present for the inquiry, in knowing that the answer to one of the oldest and grandest questions there is may be taking shape in observatories and data centers around the world even now. We may not live to see the question fully resolved, but we live in the era when it became answerable. And that is a remarkable thing to be present for. There is something worth pausing on in the deep symmetry of this whole picture, the strange and beautiful mirror image quality of it, because it reveals something about the kind of universe we live in. The big crunch, if it happens, would be the expansion run backward, the great outward rush reversed into a great inward fall, the cooling reversed into heating, the spreading apart reversed into a crushing together, the entire history of the cosmos, retraced in reverse toward a hot, dense finale that mirrors the hot, dense state from which the expansion began. It is a picture of profound symmetry, the universe's story bracketed by two extremes of heat and density, the beginning and the possible end as mirror images of one another, with the long, cool, spacious middle, the era we happen to inhabit, stretched out between them. This symmetry is not merely poetic. It reflects something real about the physics, the way the collapse would genuinely retrace the conditions of the early universe in reverse, the hot, dense state from which the expansion began, and the hot, dense state toward which a collapse would head are, in their physical conditions, strikingly similar, both characterized by extreme temperature and density, both regimes where matter cannot hold its familiar forms, both lying at the edge of what our theories can describe. In between stretches the vast cool era of structure, the only kind of era in which galaxies and stars and worlds can exist, the only kind of era hospitable to complexity of any sort. The universe, in this picture, has a shape to its whole history. Extreme at both ends, mild in the middle, a long, cool, habitable expanse bracketed by two fiery limits. And everything that has ever happened that we would recognize as interesting, all the structure, all the richness, all the slow unfolding of cosmic complexity, belongs to the mild middle, the only place in the universe's history where such things are possible. It is humbling and clarifying to realize that the conditions that allow for any complexity at all are confined to this middle era, this cool, spacious chapter between the extremes. At the fiery beginning, it was too hot and dense for structure. In a fiery collapse, it would be too hot and dense again. Only in the long, cool middle, the era of expansion and moderate temperature, can matter organize itself into the rich forms we see, galaxies and stars, and the intricate structures within them. We are, in the most literal sense, creatures of the temperate middle of cosmic history, able to exist only because the universe is, for this long stretch, neither too hot nor too dense, neither at its fiery start nor at its possible fiery end. To contemplate the Big Crunch is to recognize the boundaries of the hospitable era and to appreciate that we live within those boundaries in the one long chapter where a universe can hold such things as us, and it places our own moment in a striking light. We live, if this picture holds, in the expansive middle chapter of the cosmos, the long, cool, open era between the fiery beginning and the possible fiery end. The spacious age in which galaxies have formed and drifted apart, in which stars shine and worlds turn, in which the universe is large and cool enough for all the rich structure we see to exist. The hot, dense extremes, the beginning and the possible crunch, are the brackets. We live in the vast, mild, expansive text between them. It is in this cool, spacious middle era that everything we know and love has come to be, that the universe is hospitable to structure and complexity, that there is room for galaxies and stars, and the slow unfolding of cosmic history. We are creatures of the expansive middle, living in the long, open chapter between the extremes. There is a kind of perspective in this that can be steadying rather than frightening. To know that we inhabit a particular chapter in the vast story of the cosmos, neither the fiery opening nor the possible crushing close, but the long, cool expanse between, is to feel located in something immense and meaningful, a participant in a grand unfolding far larger than ourselves. The possible Big Crunch, rather than threatening this, frames it, gives it shape, reminds us that our era is a chapter with its own character, the spacious, cool middle of a story, whose ending, if it ends in collapse, lies unimaginably far ahead. We are not at the end. We are not near the end. We are in the long, rich middle, and the contemplation of how the story might eventually close only deepens the sense of wonder at the chapter we are fortunate enough to inhabit, and the contemplation of cosmic fate, far from making our small lives feel meaningless, can actually sharpen our appreciation of them. When you set your own life against the immense backdrop of cosmic time, against the billions of years of expansion and the possible billions of years of collapse, you might expect to feel diminished, reduced to insignificance. But the opposite response is just as available and far truer to the situation. The vastness of cosmic time, the sheer scale of the universe's story, can make the brief, warm, vivid reality of your actual life feel all the more precious, all the more remarkable. A flicker of warmth and awareness and experience set against an almost infinite backdrop, rare and fleeting and therefore valuable beyond measure. The possible end of the universe, unfathomably far away, does not diminish your life. It throws it into relief, a small, bright moment of being in the long, grand story of the cosmos, all the more worth cherishing for its brevity and its place in something so immense. This is, in the end, perhaps the most valuable thing that contemplating the fate of the universe can give us. Not dread, but a heightened sense of the preciousness of the present. The galaxies will do what they will do over the unimaginable ages, expanding or eventually collapsing, following the deep physics of dark energy and gravity across spans of time we can barely name. None of that is in our hands, and none of it touches the immediate reality of being alive right now, in this moment, in the warm and vivid present. And against the backdrop of all that cosmic vastness, this moment, your moment, the simple fact of being here and aware, the cool, spacious middle of the universe's story, becomes something genuinely remarkable. A flicker of warmth and consciousness in an immensity of space and time, rare beyond reckoning, worth treasuring, precisely because it is so brief and so small against so vast a backdrop. There is a long tradition of finding, in the contemplation of cosmic immensity, not despair, but a deepened gratitude for the here and now, and the Big Crunch fits naturally into that tradition. To know that the universe is so vast, that its history is so long, that its possible fates are so grand and so distant, is to be reminded of how extraordinary it is to exist at all, to be a small, conscious part of so immense a cosmos, present for a brief, warm moment in the long unfolding of everything. The end of the universe, whatever it may be, lies unfathomably far ahead, and the beginning lies unfathomably far behind. And we are here now, in the brief, bright middle, able to look out at the whole vast sweep of it and wonder. That is not a reason for sorrow. It is a reason for gratitude, and for a kind of quiet joy at the sheer, improbable privilege of being here to think about it at all. It is fitting that thoughts like these come most naturally. In the quiet of the night, when the day's concerns fall away, and the mind has room to drift out toward the largest questions there are. In the busyness of daylight, the fate of the universe is an abstraction, easily set aside. But at night, in the stillness, lying in the dark, it becomes possible to feel the genuine scale of it, the strange grandeur of knowing that the cosmos has a history and may have a finale, that the expansion carrying the galaxies apart tonight might in some unimaginably distant future slow and halt and reverse into a great collapse. The night is when these vast contemplations breathe, when the mind can hold the whole sweep of cosmic time, from the hot dense beginning to the possible crushing end, and find in it not terror, but a profound and quiet wonder. And as you hold that thought tonight, let the comfort of distance settle over it, the comfort of knowing that whatever the universe's ultimate fate, it lies so far ahead that it cannot trouble your rest. The galaxies are flying apart right now, gently as they have for billions of years, and they will go on flying apart for billions more. And even in the scenarios where they someday turn around and fall back together, that turning is so unfathomably remote that it has no bearing on this night, or any night you will ever know. The universe is not about to collapse. It is expanding calmly, vastly, as it has all along, and the possible crunch is a feature of a future so distant that between now and then lies more time than has passed since the beginning. You can rest entirely easy beneath the expanding sky, and there is something quietly beautiful in that very expansion, in the fact that the universe you live in tonight is, at this moment, growing, opening, making more room. The same process that might, in some unimaginably distant future, reverse into collapse is right now doing the opposite, gently carrying the galaxies apart, enlarging the cosmos, the night sky deepening and widening with every passing moment. You live in the expansive era, the time of opening rather than closing, of growing rather than shrinking, and the universe around you tonight is in its long, slow, spacious phase of growth, calm and vast and unhurried. Whatever may come in the deep future, this is a universe that is right now expanding around you as you rest, a cosmos in its open and generous middle chapter, making space rather than crushing it. Let that be a comfort rather than a concern. The galaxies drifting apart tonight are not racing toward any doom. They are simply continuing the ancient, gentle expansion that has been unfolding since long before there was an Earth to watch it, and that will continue, in all likelihood, for ages beyond ages more before anything changes. The expansion is slow and serene and almost unimaginably patient, and it asks nothing of you. You can lie beneath it exactly as you would lie beneath any peaceful night sky, knowing that the cosmos above you is in no hurry, that its possible distant fate is precisely that, distant, and that for now, and for all the time that could ever matter to you, the universe is simply, gently, calmly expanding, holding you in its long, quiet middle chapter as you drift toward rest. So let the great expansion hold you gently tonight, the same expansion that has been unfolding since long before the Earth existed, and will go on unfolding. Long after this night has passed into memory, you are living in the cool, spacious, expansive middle chapter of the cosmos, the long open era of galaxies and stars and quiet nights, immeasurably far from any fiery beginning or any crushing end. The universe around you is calm and vast and slowly growing, the galaxies drifting apart in their ancient unhurried way, the night sky dark and deep and serene above you. Whatever the final fate of all things, it is not tonight's concern, and it is not yours to carry. It is simply a magnificent question to wonder at, and then to set gently aside. And perhaps that is the right way to carry any of the great cosmic questions, lightly, with wonder rather than worry, as gifts for the contemplative mind rather than burdens for the anxious heart. The fate of the universe is one of the grandest things a person can think about, and it is yours to think about freely, to turn over in the quiet of the night, to marvel at, precisely because nothing about it presses upon your actual life. You are not responsible for the fate of the cosmos. You cannot change it, and you do not need to. It It will unfold over spans of time so vast that your whole life and the whole life of your world is the briefest flicker within them, and that frees you to enjoy the question purely as a thing of beauty and mystery, the way you might enjoy the sight of a distant mountain range or the depth of a starry sky, something grand and far away and wonderful to behold, asking nothing of you but your wonder. So hold the Big Crunch that way, as one of the great wonders, and let it sit alongside all the other vast and beautiful things the universe contains, the galaxies and the nebulae and the deep reaches of space and time. It is a magnificent possibility, the idea that everything might one day fall back together in a final fiery crush, and it is worth knowing about, worth marveling at, worth letting expand your sense of the strangeness and grandeur of the cosmos you inhabit. And then, having marveled, you can let it go and return your attention to the warm and immediate world around you, carrying just a little of the wonder with you, a deepened sense of living in a universe far vaster and stranger, and more dramatic than the quiet night sky would ever suggest. There is a deep peace available in that, the peace of holding the largest questions lightly, of contemplating the fate of the universe without being burdened by it, of letting the cosmos be vast and mysterious and ultimately unhurried while you rest in your small, warm corner of it. The expansion will continue tonight, silent and gentle, the galaxies drifting apart across the dark. And whether the universe ends in the unimaginable future, in a slow, cold fade or a distant, fiery collapse, none of it asks anything of you now, in this moment, in this quiet night. You can let the whole grand story unfold in its own immense time, while you turn toward sleep, beneath a sky that is for all the ages of your life, and far beyond, simply, calmly, peacefully expanding. So let your thoughts slow now, and let the vast question settle into the quiet of the night. You have traveled tonight across the entire span of cosmic time, from the expanding universe of the present to the possible turnaround in the unimaginable future, through the great reversal, the gathering collapse, the brightening sky, the rising heat, all the way to the crushing finale and the honest mystery of what lies at the very end. You have seen one of the most dramatic fates the cosmos could face, and you have understood it not as a nightmare, but as a real scientific possibility, balanced against the question of dark energy, hanging on the deepest mystery in cosmology. And now you can let it rest. Picture it one last time softly, without fear. The universe, vast and cool and expanding, the galaxies drifting apart across the dark as they have for billions of years. And the distant possibility, unimaginably far ahead, that the expansion might someday slow and halt and reverse, the cosmos falling back together in a fiery finale beyond the reach of our current understanding. It is one of the grandest questions there is, the ultimate fate of everything, and you have held it tonight and looked at it and seen both its drama and its distance. The universe will go on expanding quietly for ages beyond counting. Whatever its final fate may be, there is nothing you need to do with this knowledge tonight. The cosmologists will go on measuring the expansion, probing the nature of dark energy, working to learn whether the universe will expand forever or someday collapse, pursuing the question at the very frontier of what we can know. The galaxies will go on drifting apart, silent and serene, as they have since long before you were born. And you can simply let it all be, the vast expansion, the distant possible collapse, the grand unfolding story of the cosmos, and turn toward rest, a small, warm being in the cool, spacious middle chapter of an immense and ancient universe. Let the expanding sky hold its quiet mystery above you. Let the cosmos be vast and unhurried and ultimately gentle in its slow, ancient growth, and let the question of its final fate be a distant wonder, rather than a present weight. You are here, safe and warm, living in the long open era of galaxies and stars, immeasurably far from any beginning or any end, free to marvel at the grand sweep of cosmic time, and then to close your eyes and rest. The universe is expanding, calmly as it always has, and it will go on expanding through this whole quiet night, and through all the nights of your life, and for ages beyond imagining, carrying the galaxies gently apart across the peaceful dark, exactly as it does now, exactly as it will, long after this quiet night has passed into morning.